Okay, so welcome back. The plan for today is to start chapter 5 on discrete probability distributions. Hopefully make it a good bit of the way through section 5.1. We were planning to start this last Wednesday, but unfortunately I wasn't feeling too well the end of last week, so I did cancel my classes Wednesday and Thursday. Um, so the makeup for that class is to watch the section 4.4 video. I've popped that onto the end of our YouTube playlist, and I have the link here as well. Let me see if this will copy nicely. I don't know if Zoom will let me just post a random link into the chat, but we'll see if it will. Okay, it looks like it did let it go through. All right. So there's the direct link to the video, or you can check the YouTube playlist for the 24 fall probability and stats. And that's just a run through of section 4.4 on counting. So it rehashes a couple of the things we talked about and then goes through the rest of 4.4. So take a look at that section when you get a chance. Um, and then this Wednesday, we'll work through parts of sections 5.2 and 5.3. And I'll also probably end up posting a supplement on that as well. So this section 4.4 supplement's kind of short. It's maybe about a half of a class length. And depending on how far we get on the 16th, I'll probably post a bit of a supplement on 5.2 and 5.3 as well. Then on the 21st, we originally had a makeup day scheduled. We were running a little bit behind, and then with losing the class, we're running a bit behind now. But nicely enough, we had this buffer day, this makeup day scheduled the 21st. So we'll just slot Bayes' theorem into there. Bayes' theorem is one of those topics that it's somewhat tangential to the course, so we could go more in depth on it or less in depth, and we'll cover it in a little bit less depth. Leave a couple of problems off and so on. So that's what we'll do on the 21st. And on the 23rd, we'll be into the normal distribution chapter 6, and that'll bring us back to right on schedule according to the course schedule. The Examity practice exam is available, and a few folks have been able to log in, get Examity up and running, make that all work together. So everything should be working just fine. Like I mentioned before, the Proctor U system, there are some workarounds we have to figure out, so we're reverting back to the Examity system for this semester. And Examity does seem to be working just fine. That's kind of the tried and true system. So, but that being said, make sure that you get on and do that well before the next actual exam. So, you'll need to kind of go through Blackboard, log on to Examity. There was a post with all the details. But log on to Examity, kind of get an account set up first. If you don't have one already, you might have one from another course. And then, take the Examity practice exam. It's not, it doesn't count towards your grade. It's not meant to, test your stats knowledge or anything like that. It's really just kind of an exam with some dummy questions in it to just make sure that you can do the process of working with Examity to get the exam started up and all that, make sure all the tech is working out right. Make sure you can submit the exam and the Examity session and all of that, make sure all that goes well. So to make sure that all that works, and also just so that you have a chance to do it before the actual exam day, it takes a little bit of the stress off having done it once already. So make sure to do that fairly soon. It shouldn't take very long to do. But there are a couple little tech details like getting the browser extension added into Chrome, stuff like that it was just nice to do once and kind of have it already done. And then lastly, the quote of the day today. This was actually something that was posted in a Facebook group that I'm in recently. And at first glance, I thought it was a dumb question. And the more I thought about it, the more I actually really enjoyed this question. And I thought it was a deeper question than it at first seems. And I don't know, I'm 39 years old, so maybe I have a different perspective on this than some of you who are, closer to 20 years old. But I think even at 20 or in your 20s, you can maybe appreciate this a little bit. Oh wait, so question here. My Examity practice exam isn't prompting me with the password to take the exam. Is anyone else having the problem? So it's not asking you for a password? Is that what you're saying?
It is asking me for a password, but
Okay.
I think in your post you said that it'll prompt you to input that password. And I'm not getting anything. I tried my password for my Examity account and I just can't seem to access.
Yeah, so Examity will enter the password for you. Did you uh add in or download or whatever the browser add-on, the browser extension for Examity?
I did, but I'll double check everything there.
Okay.
That could be the issue.
Yeah, the Examity browser extension and the pop-up on it's usually on the right-hand side, I think. There should be like I think it's a yellow kind of like oval button that says something like enter password. And whenever you have your cursor on the like exam password text box for the WebAssign exam, then you should be able to click that button and it should just pop the password in there for you. And then you should be able to get in. So if you're having trouble with that, let me know. I think I have a couple of screen caps that I can also either post or email to you, and hopefully that would clarify things. But yeah, so it's a combination of that browser extension with the WebAssign password field. So the browser extension is what you hit the enter password button, and then that should pop the password into the WebAssign system for you.
okay, thank you.
Yeah. Yeah, but both of those have to be up at the same time. So yeah, and that's the reason for this practice exam to get kind of some of these little details ironed out. So you've gone through it once, you kind of know how it works. It can be a little bit like, whatever, patting your head and rubbing your tummy, like the first time you do this, you got to do things, kind of just right. Um, but once you do it, it's like, oh, okay, that's how it works. So I really wish I've tried to do this. I really wish I could go in as a student and just make a recording of myself doing all of this to take the exam. Um, we like cannot figure out any way to make that happen. Under our old Blackboard system where everything was hosted on our local physical hardware, we were able to do that. I actually had a student account that was not my faculty account, and I could log in and pretend I was a student and do all this stuff. We went to the cloud-based, which is great for things like stability and reliability and speed and all that, but we can't have those kind of accounts anymore. And um, so I wish I had a better, option for you. But that is where I think it's HACC, Harrisburg Area Community College. There's a link in the Examity practice exam announcement, and they kind of walk through that. Somehow they were able to, set their system up with a student account and that you show things from the student side. Um, so you can check that out. That kind of gives you a little more of a walkthrough as well. I think they enter a password in that one, if I remember right. Um, yeah, good question though. But on the quote of the day, yeah, again, I kind of thought that my first thought was this is kind of a silly question. Um, but I actually thought about it and I thought it's actually a much deeper question um, than maybe at first seems. And so I replied to the person, told them what my thoughts were about it. Um, but it says, if you could teleport into the future and teach your older self anything, what would it be? And of course, the kind of silly thing is that the trope, of this is if you could teleport into the past and teach your young self anything, what would it be? It's like, yeah, but that's kind of a tired question, right? I mean, people either say like, oh, what the lottery number would be or something, or they, give their like best piece of wisdom or whatever. But I think there's a wisdom in being young as well, right? Before before maybe your sense of the world was kind of warped with different experiences and so on, what did your younger self see that was maybe more true about the world than maybe your current self sees? I think is kind of what the question is getting at. And I think it's a really interesting question to kind of ask yourself. I'm certainly not asking anybody, here, but maybe it's a worthwhile thing to think about or reflect on, I think. Uh, so I just thought it was really cool. So I kind of made that the quote of the day for today, that question. All right, so moving on to chapter 5. So no PowerPoint for chapter 5, or really for most of the rest of the course. Most of everything from here on out is going to be kind of paper and pencil, so to speak. So moving on to chapter 5, discrete probability distributions. Now, one thing that we remember from chapter 4, well, a couple of things remember from chapter 4. One was that we've switched gears from chapters 2 and 3, which was very empirical, very real world based, where we said, roughly speaking, I don't know anything about mu, but I maybe know about X bar, right? I don't know the population parameters, but I have some real world data, some data about the real world that I can calculate maybe sample statistics from and make guesses at the population parameters. Chapter 4 kind of flipped things around and said, well, in chapter 4, we know all of the underlying mechanics of the system. We know all of the population stuff, basically. We're saying, we roll a die, it can only come up 1, 2, 3, 4, 5, 6, and they are equally likely. But what we don't know is on one roll of a die, what might it come up, right? I mean, on one roll of a die, it might come up 1 this time and 4 that time, right? I don't have the real world data, so to speak. I have the population level uh, information. Now, chapter 4 also had a pretty severe restriction. When we set up our idea of a sample space and so on, we said that, well, our sample space to calculate probabilities in chapter 4 had to consist of equally likely outcomes. And we had to sometimes really bend over backwards to make our outcomes equally likely. And there are some examples where it's not really natural to have equally likely outcomes. So what if I want to take the ideas from chapter 4, the ideas of probabilities and so on, and maybe generalize that? Specifically, what if I want to generalize it to where I have non-equally likely outcomes? Well, I might want to construct something which we call a probability distribution, or in this case, a discrete probability distribution. Discrete reminds us of the chapter 1 discussion on types of variables and so on, where we had discrete quantitative variables and continuous quantitative variables. And kind of roughly speaking, the distinction between the two was discrete variables, there's a next one, where continuous variables, there's not, right? If I have number of students in a classroom, there could be 5 students. What's the next possibility after 5? The next one is 6. If I'm talking about a person's height, a person could be 5 feet tall. What's the next possible height? Well, the next possible height isn't 6 feet tall, or it's not 5 foot 1 inch, or it's not, 5 feet and 0.1 inches. There's kind of always another viable height in between any two heights that you might write down. So that's what we mean by discrete here, versus in chapter 6, we'll look at continuous probability distributions. So chapter 5, all about discrete probability distributions, where there's this concept of a next possible outcome. And one of our classic examples of this, a discrete set of outcomes, was the number rolled on a die. So I have numbers 1, 2, 3, 4, 5, 6 on a die, and those are my possible outcomes. Now, last time I said I had a fair die. 1 through 6 were equally likely to come up. But here, maybe I have, an unfair die. Maybe it's loaded in a certain way to make it come up this way, or maybe it's just poorly manufactured and it's not really a fair die. So here, maybe I just know inherently somehow that the number 1 comes up 10% of the time, the number 2, 10% of the time, 3, 20%, 4, 25% of the time, 5 and 6, 20% and 15% of the time, respectively. Now, our outcomes are discrete quantitative, 1, 2, 3, 4, 5, 6, and our probability is sum to 1. That was our law of total probability, that the probabilities of each of the outcomes all added together have to sum to 1. So if I do 0.1 plus 0.1 plus 0.2 plus 0.2, so that's 0.6. And then if I add to that 0.25 and 0.15, 0.4, 0.6 plus 0.4, it does indeed sum to 1. So I'll just note that here. Sum equals 1, check. And I have discrete quantitative outcomes. So these aren't outcomes like red, blue, green, or something like that. These are discrete quantitative outcomes. They're also not outcomes like heights, like 5 foot 1.3 inches or something like that, discrete quantitative outcomes. So this is a discrete probability distribution. And we see that we have a lot more flexibility here than in chapter 4 because I can kind of assign really any distribution of probabilities that I want to this set of outcomes, as long as I scale it appropriately so that things sum to 1. But I can make any proportion of ones through sixes occur. So it's not just that I have to have 1, 2, 3, 4, 5, 6 occur equally likely. Now I can, I guess, if I wanted to really brute force it, if I really wanted to like whack this thing with a sledgehammer and make it look like chapter 4, I guess I probably could do that. I could imagine, let's say having 100 slips of paper. So I have 100 slips of paper, and maybe I could write the number 1 on 10 of them. And the number 2 on 10 of them. And the number 3 on 20 of them. And so on, right? The number 4 on 25 of them, the number 5 on 20, the number 6 on 15 of them. Throw all of those slips of paper into a bag, shake it up. Now each slip of paper is equally likely to be drawn. And then I could draw a slip of paper out and see what number I get. So I could have, whatever my first slip of paper that has a number 1 on it, my second slip of paper with number 1, through the 10th slip of paper that has a number 1, the 11th slip of paper would have the number 2, the 12th slip would have a number 2, and so on. So I really could, if I wanted to, kind of force this into the mold of chapter 4. So a lot of the theories and basic ideas in chapter 4 are going to apply here as well. This does tie back to chapter 4 that way. But we have a lot more flexibility here that, at least in our kind of basic way of thinking about outcomes, 1, 2, 3, 4, 5, 6, rather than having to think of outcomes like a bunch of slips of paper or something. In our basic way of thinking about outcomes, they're not equally likely. And one thing we've talked about already is there's this fallacy, this generally false way of thinking related to probabilities. And it's the idea that, say, for instance, if there are 2 possible outcomes, the chance of either one is 50-50, or if there are 6 possible outcomes, they have to be equally likely. This is clearly not true, right? We can come up with absurd examples like that's like saying if I buy a Powerball ticket because I can either win the Powerball or not win the Powerball, there are 2 outcomes. It's 50-50 that I win the Powerball. Well, of course not. So we see that, in the general case, outcomes are not equally likely. It's actually a fairly special case where outcomes are equally likely, or we have to really go a long way to manufacture that kind of an equal likelihood system. Okay, so let's take a look at a couple of examples here. If we want to think about, say, flipping a coin, getting heads or tails, if I want to make a discrete probability distribution out of this, let's say that I have an unfair coin where heads comes up 70% of the time and tails 30% of the time. If I wrote something like, tails 0.3, heads 0.7, well, that wouldn't be a discrete probability distribution because tails and heads are not discrete quantitative values. We want in a few minutes here to be able to do things like compute an average more or less, or compute a standard deviation. And if I have things like tails and heads and so on, I can't really do that. So one thing that we often see is that in cases like this, where we have kind of the natural observations are maybe qualitative, we often have a variable that maybe is counting the number of something, right? So I could let X be a variable counting the number of heads on one flip of an unfair coin. And now if I get tails on my single flip, I got 0 heads on that flip. So that's X equals 0. And if I flip and get a heads on that one flip, I got 1 head on that flip. So that's X equals 1. So I see that I know that tails comes up 30% of the time, heads 70% of the time, and tails corresponds to X equals 0, getting 0 heads on that flip. Heads corresponds to X equals 1, getting 1 head on that flip. And by associating those two ideas, the tails is related to, say, a probability of 0.3 and a number of heads on one flip and an X outcome of 0. And similarly, heads being related to 0.7 and X equals 1. I see that I do end up with a discrete probability distribution. X equals 0 or 1, that's a discrete quantitative variable. And the probabilities 0.3 and 0.7 do add up to 1. I could also, for instance, think of making a bet one way or the other. So for instance, if I bet on heads and the probability of heads is 0.7, then again, I have kind of a structure like this. Tails is associated with probability of 0.3, heads with probability of 0.7. But if I bet $1 on heads, meaning that if the coin comes up heads, I win $1. So if the coin comes up heads, I win $1. And the coin comes up heads 0.7 proportion of the time, or 70% of the time. So I win $1 70% of the time. And similarly, I lose $1 when the coin comes up tails. The coin comes up tails 30% of the time, so I lose $1 30% of the time. So that's something that folks sometimes struggle with in examples like this, is when you have kind of an underlying maybe qualitative variable like tails or heads, there are different ways to translate that in a sense to a quantitative variable. And we have to, really pay attention to the context. Are we looking at, say, a bet? Are we looking at, say, a counting number or something else? Okay, so what is the expected value? Well, in chapter 5, we call it the expected value, but really it's just the mean of the distribution. It's just the average. It's actually a little bit of a misnomer because the expected value might make you think of something like, oh, I don't know, maybe like a median, or even more likely, maybe a mode. Which one are you most expecting to see or something like that. That's not really what it is, though. The expected value is the mean of the distribution. It's the average. And we can actually kind of think of, well, not just really kind of think of it, it really is equivalent to a center of mass of the distribution, where mass is represented by probability and location by outcome. So if I were to say take my die roll up here, just copy that down. If I were to imagine a weightless bar that I can put weights on top of, and if I had little indices along here, and I could imagine, for instance, that I have a weight of, say, 0.1 grams or 0.1 kilos or 0.1 pounds or whatever, a weight of 0.1 at position 1. So this weight is 0.1. I have a weight of 0.1 at position 2. I have a weight of 0.2 at position 3. OneNote is just trying to be super helpful today, making all kinds of extra lines everywhere. 0.25 at 4, so a little more weight here. Uh, 0.2 at 5. and 0.15 at 6. So if you imagine this set of weights sitting on this weightless bar, and then you might ask the question, where should I put a balance point or a fulcrum to make the thing balance? If I put it, here, obviously it's going to tilt to the right and fall over. If I put it, over here, it's going to tilt to the left and fall over. We want to position our fulcrum at the center of mass at the balance point. We want to position it in a way that the two moments equally oppose one another. And I don't know, just at a kind of a glance, maybe if I put it right in the middle here between 3 and 4, well, this stuff on the right over here is bigger than the stuff on the left. I think it's going to want to go this way just a little bit. So I think I've got to put it a little bit further to the right than right in between 3 and 4, maybe like somewhere like right around 4. We'll actually figure out what the actual location is here in a little bit, but just, looking at this pictorially, maybe expected value of X, the mean is something like that. This is actually going to be kind of an important idea when we move into chapter 6 as well, because when we start talking about continuous distributions, we're going to really leverage this idea of mass being equated to probability and location being represented by outcomes. So we're really going to kind of lean into this more in chapter 6. Right now, it's just kind of a nice little analogy. But the expected value is, which we also refer to as mu, the mean, is computed this way. X1, outcome 1, times probability of X1, plus outcome 2 times its probability. We take each outcome, multiply it by its probability, then we add all those together. You might actually recognize this as something like a center of mass equation from, high school science or college science or whatever, college physics or something. You might actually recognize this and say, oh yeah, I remember like center of mass kind of had a setup that looked like this. Now, center of mass kind of takes all of this stuff and divides by the sum of the masses, which would be like probability X1 plus probability X2 and so on, plus probability of Xn. But remember that our sum of all of our probabilities just equals 1. So we actually don't need to explicitly write out this whole denominator. That's one of the really nice things. Oh, okay. Undid too many times and it's not happy now, so let's erase that. That's one of the nice things about our probability being constrained in such a way they must sum to 1, that we have this kind of weighted average down here, but we don't have to worry about the denominator. The weights are naturally set up. These weights, these probabilities are naturally set up so that they all sum to 1, and we don't have to worry about dividing by the sum of the probabilities. Okay, so let's go through this and actually compute this. So remember, what do we want to do? We want to take each outcome multiplied by its probability, and then we want to add those all together. So let's look at, for instance, the scenario where I have X counting the number of heads on one flip of an unfair coin, and this coin comes up heads 70% of the time. So if I take the outcome 0 times its probability 0.3, that gives me 0. 1 times 0.7 is 0.7. And if I add them up, I get the expected value of X is 0 plus 0.7 is 0.7. Kind of similar to chapter 3, when we're going through these calculations, I like to kind of start with my probability distribution and append a couple columns onto the end to keep things kind of sorted out, keep them nice and straight. So I have my expected value of X or mu, the mean of 0.7. So in other words, on average, I get 0.7 heads per flip. Now, again, we call this the expected value, but note that we can never actually get 0.7 heads per flip. It's kind of a silly name, right? Like, I don't know, if I had to name this, at least looking back, I probably would have named it something different. So calling it the expected value, we might, think just looking at the name that the answer maybe should be 1 because that comes up more often. I don't know. But the expected value is 0.7 heads per flip. What do we mean by that? Really, what we mean by that, and this is the frequentist perspective. Again, we'll talk about the Bayesian perspective next week. But what we mean by that is kind of this idea. So I have this probability experiment, this flip a coin, count the number of heads I get. In other words, if I get a tails, 0, heads, 1. And that's my probability experiment. Now imagine I run that probability experiment. I get an answer, I write it down. I run the experiment again. Same scenario, same setup, everything. I get an answer, I write it down. Maybe I run the experiment 10,000 times. And then I look at the average number of heads I get per experiment. I look at the total number of heads divided by 10,000 experiments. I would expect that number to be very close to 0.7. That's really what this is. When we talk about the mean or the expected value, it's kind of like a long-term, like running average in a sense. If I were to repeat this experiment 100 times, 1,000 times, 1,000,000 times, a whole bunch of times, and I were to aggregate, all of the zeros I got, all the ones I got, and so on, I would expect the average result to be 0.7. Or if I come down here, I can look at what if I bet $1 on an unfair coin? So I have this coin that I know is unfair, comes up heads 70% of the time. So I go to my friend or maybe my enemy and say, I'll bet you $1 on the flip of this coin. If it comes up heads, I win $1. If it comes up tails, I'll pay you $1. So what would be the average winning here? What would be my average winning? Well, the outcome -1 when it comes up tails and I lose $1 occurs 30% of the time. So for my expected value, the first thing I want to do is multiply outcome times probability. This gives me negative 0.3. And then the other outcome, +1, when I win $1, that happens 70% of the time, plus 0.7. My expected value then is negative 0.3 plus 0.7 is plus 0.4. Maybe we should throw units onto here. These X's would be in units of dollars, and the probabilities are unitless quantities. So again, what is my expected win per play of this game? Plus 40 cents. I expect to win 40 cents per play of the game. If I play the game once, I don't care how good the odds are in my favor. Even if it's 99% to 1% that I win, I either win $1 or I lose $1. It's one of those two choices. But again, what is the expected value saying? It's saying that if I played this game, 100 times, 10,000 times, some large amount of times, and then I added up all my winnings and averaged it across those games, on average, I would win about 40 cents per play of the game. Sometimes I win $1, sometimes I lose $1, but I would win $1 more often than I would lose $1. So I'd end up net positive. Right. As kind of a side note, this is how I see like life decisions a lot of the times, right? I mean, sometimes you make the good decision and it comes out bad, like just kind of bad luck in that case. Sometimes you make the good decision, it comes out good, and also vice versa. Sometimes you make a poor decision and get away with it, and sometimes you make a poor decision and get hit get hit with the consequences. If you make, lots of good decisions, you won't always come out on top. But if you come out on top more often than not when you make a good decision, like kind of the long run average, you're going to end up doing pretty well, right? So if you make a good decision once and it doesn't come out well, don't get discouraged because of that. Life is, for the most part, kind of a game of averages. Make the good decision, make the, bet on heads in this case. And even though you might bet on heads and lose a dollar once in a while, you're going to win the dollar more often than you're going to lose the dollar. Um, and in life, those benefits compound as well. When you say metaphorically win that dollar, it makes it a little easier to win the dollar next time. Figuratively speaking. Okay, so let's say we go up to our friend and we have our friend or enemy, I suppose. We're trying to trick them, so maybe they're not our friend. Um, let's suppose I have my unfair coin that I know is biased towards heads. It comes up heads 70% of the time, tails 30% of the time, and I say, hey, you want to play a game where we flip a coin, but my friend or enemy knows that I have this unfair coin. Well, I mean, I suppose one thing they could just say, no, I don't want to play your game, but I don't know, if we're in a desert island and we have nothing better to do, they could say, well, this is an unfair coin. To make it fair to me, we'll use a different coin. We'll use a fair coin because they're not going to want to give me this long-term benefit, right? This kind of house advantage, so to speak. They're not going to want to give me this edge over them. So they're not going to be happy playing this game with an unfair coin that they know gives me a benefit. So one thing they could do is they could demand, no, we're going to use a fair coin. Okay, fair enough. They could do that. What if we don't have a fair coin available? What if we're stuck with these probabilities? An interesting question. This is a side question, an exercise, something to think about. What if I want 50-50 with an unfair coin? Can you come up with not just one flip, but maybe a sequence of flips or a way to play the game that gives each person a 50% chance of winning the game? And as kind of a hint, this might involve, say, two flips of the coin where, you know, where a different person gets a different heads or tails on each flip, something like that. So give this a little bit of thought. What if I want a 50-50 chance of each outcome, but I only have an unfair coin to flip? So it's an interesting little question. There are a couple of little intricacies, like what would you do in this situation or that situation if they come up? But that's just kind of a side note. But another way that we could make this fair, so one way to make it fair is to kind of force the probabilities to be 50-50 somehow, either by changing up the nature of the game or using a different coin or something. But if we're on a desert island, we only have this one coin and we only have time for one flip, whatever, we say, okay, I'll accept the lower chance of winning. My opponent says, I'll accept the lower chance of winning. But to make things fair, maybe they demand a higher payout when they win. So they win a lower proportion of the time, but when they win more money. And me with who gets heads, I win more often, but when I win, I get less money than they do. So we could ask, well, if D is the number of dollars that we're going to pay them when they win, for this to be a fair game, in other words, for it to be zero expected value, so that neither one of us has a long run advantage. If we played this game, 10,000 times on average, we would both come out to have very close to no net win or net loss. What should I choose that payout to be? What should I agree to pay my opponent when they win to offset their lower probability of winning? Well, what can I do here? I have this variable D that's in my outcomes. I pay them D when they win, and they pay me $1 when I win. They win with probability 0.3, I win with probability 0.7. This is still a discrete probability distribution, no problem there. Probabilities add to 1. We can do the exact same thing we did up above. We can calculate the expected value as negative d times 0.3. That's negative 0.3 d. And then positive 1 times 0.7 is positive 0.7. OneNote just really wants to connect my zeros to my decimal points today. I don't know why. And my expected value then is 0.7 minus 0.3d. And to impose that this is a fair game, I'm going to set this equal to 0. Or this tells me d is, well, it's 0.7 over 0.3, or that's 7/3, or about 2.33 or $2.33. So in other words, if we wanted to play this game and my opponent knew that I have this unfair coin that was weighted 70/30 in my favor, they might demand a $2.33 payout when they win. They might say, okay, I'll accept the lower probability of winning, but you've got to pay me more to offset that, right? The most extreme case of this is something like the Powerball, right? Where it's like such an incredibly low chance of winning, 1 in 100 million or something like that. But if you win, you get an enormous amount of money, right? So would I pay $1 for a lottery ticket if I had a 1 in 100 million chance of winning, and if I win, I get $10? Well, no, that's not worth it, right? But if I say, okay, if I win, I get whatever, $1 billion or $500 million or something, well, maybe that's worth it to me then, right? Maybe in some sense, the two balance out in my mind. That I know that it's almost impossible for me to win, but if I do win, it's an absurdly large amount of money. And there's, of course, a lot of psychology that goes into that kind of stuff as well. Like we talked about um, in one of our last classes, that, we're kind of terrible at naturally judging outliers. And if you said, a 1 in 100 million chance of winning $500 million, or a 1 in 175 million chance of winning $300 million, we probably, look at that about the same. So it's like basically impossible to win more money than I can imagine what I would do with. So like, uh, how do you actually value such a proposition? That's a whole other question that's that's dealt with in things like behavioral finance, behavioral economics, super interesting fields that combine the kind of hard math alongside the psychology. But we see here that we could, again, kind of balance the fairness of the game by changing the payout or the outcomes, or by changing the probability. We could change, if we have two unequal weights, let me just draw a new line here. If we have two unequal weights, we start it. If I have a weight of size 1 at position 1, I could balance it by putting a weight of the same size at position -1. Um, sorry. If I have a weight of size 0.7, instead of weight of size 1 at 0.1. If I had a weight of size 0.7 at 0.1, if I try to put a weight of size 0.3 at -1, that's not going to balance. So my choices are to put a weight of size 0.5 at -1 and a weight of size 0.5 at +1 that would balance. Or what I could do is I can move this weight of size 0.3 further out to the left. In this case, if I moved it out to something like -2 1/3, in both of those cases, my balance point would be right here at 0. Right. Either I could give this a longer moment arm, a longer lever arm, So this is less weight, but it's pushing down on a longer lever, and this is more weight pushing down on a shorter lever, or I could make the weights and the levers kind of equal. Okay, so what about an example like this one? Let me switch my share here really quickly. Oh, the calculator went onto my wrong screen. Let me get that sorted out. There we go. Now let me switch my share. Okay, so let's look at this example, number rolled on an unfair die. So I have 1 times 0.1. Well, that's easy enough. That's just 0.1. This is our same unfair die as before, right? We're just looking for the expected value now. 2 times 0.1 is 0.2. OneNote really wants to connect everything to my decimal points today. I don't know if I'm writing them funny or what. 3 times 0.2 is 0.6. 4 times 0.25 is 1.0. 5 times 0.2 is 1.0. And 6 times 0.15, well, what is that? That's 3 times 0.3, that's 0.9. And we can add these together on our calculator. Oops, 0.1 plus 0.2 plus 0.6 plus 1 plus 1 plus 0.9. Does that look right? And we get about 3, or we get exactly 3.8. Right, if we go up to our picture, we saw that if we put our balance point right between 3 and 4 at like 3.5, and I mean, at first glance, it seems to balance out pretty nicely, but I see that the 0.25 is a little bigger than the 0.2, and also these two weights are bigger than these two weights. It's probably going to tilt that way a little bit to the right. So I need to move my balance point a bit further to the right of 3.5, but probably not too far, right? It looks close to balanced. So our guess was somewhere in the ballpark of 4-ish. And that's what we saw here, right? We did the calculation and we got 3.8 out. Any questions on discrete probability distributions or expected values? Okay, let me switch back for just the time being to OneNote. I know that when it's just OneNote, it comes up a little bigger on your screen. So for those of you with smaller screens, makes it a little easier to read. Okay, so moving on to the idea of variance and standard deviation. Right, one of the aspects that we're often interested in is the mean. It's something like, in some sense, the typical data point for a data set, or in this sense, it's kind of something like the long run average. If I repeated this experiment, in this case, maybe if I rolled this die, say 10,000 times, I wrote down all of my, I rolled it once, I got a 2, I wrote down 2, I rolled it again, I got a 5, I wrote down 5. And I took that huge data set, size 10,000, and computed its sample mean, its mean. I would expect a number close to 3.8 for that. That's what the expected value is telling me. It's kind of telling me that if I constructed a sample in this manner, just repeating this experiment lots and lots of times, what would I expect the mean to be? So again, we got 3.8 from the expected value. 3.8 is not a member of the set of possible outcomes, right? I can't roll a 3.8. So I want to be very clear about that. It's a little bit of a confusing name for it, but it's more along the sense of maybe something like what would I expect the average to be, something like that. Moving on to variance and standard deviation, the other aspect that we're quite often interested in with with any kind of a distribution or data set or thing that we're studying, population we're studying, is how spread out can it be? And if you remember, when we constructed the variance in chapter 3, we came up with this idea that the variance was something like the average squared deviation from the mean. So we took each, well, in chapter 3, we're dealing with a data set with data points. We took each data point's value, subtracted off the mean, whether it was the sample mean or population mean. That gave us kind of a deviation. And then we squared that, because if we didn't square it and we added them together, they would just all cancel out. There would be a bunch of plus deviations and a bunch of minus deviations that would all net out to 0. But if we square it, we make them all positive. Then we add them together and we get something that's non-negative. Okay, so put in our new verbiage, the variance is kind of the average square deviation from the mean, but in chapter 5, average kind of means expected value. So it's the expected value of x minus mu all squared. Now let's forget about this second part here for just a second. So it's the expected value of something. Well, I know how to compute expected value of x, but what's the expected value of some function of x? Well, nicely enough, it actually works pretty easily. The expected value of some function of x, say expected value of g of x, is you just take g of the first outcome times the probability of the first outcome plus g of the second outcome times probability of the second outcome and so on, plus g of the last outcome times the probability of that outcome. So expected value of function of x, I just transform each of my outcomes using that same function and then multiply those against the original probabilities. Note that I do not do something like a g of the probability. I still want my probabilities to be weights. They still have to add to 1. So I don't want to transform them with my function. The probabilities don't get transformed. It's the outcomes that get transformed by my function. So for instance, the expected value of x squared, where here the square is inside of the expected value, it's directly on the outcome. So it's the outcome x squared, take the expected value of that. That's x1 squared times probability of x1 plus x2 squared times probability of x2 and so on. A couple of important notes on expected value variance. The expected value is linear. So for those of you who have had maybe some slightly more advanced math, you might know the importance of linear operations. They work very nicely. Basically, they split sums apart and constants can come outside of them. So the expected value of ax plus b, where x is a random variable and a and b are just some numbers. So expected value of number times x plus number. The expected value can split the sum apart. So that becomes like expected value of ax plus expected value of b. And then the a, that factor, can just come out in front of the expected value. So we get a times expected value of x plus, and then of course expected value of b, well, that's kind of just a variable whose outcome is just b 100% of the time. Of course, its expected value is going to be b. If I like have a die where like all 6 sides are just labeled b, and I roll that die 1,000 times and write down every time I'm going to get a b, and then I average my answers together, my average is going to be exactly b, right? This is the math to show that. So the expected value of ax plus b is take your first outcome, x1, apply the transformation a times x1 plus b, multiplied by its probability. Same with x2 out to xn. We can collect all of our x1 all of our xi stuff, our x1 bit, our x2 bit, through our xn bit. We can collect all of those terms that have the xi's or that have the a's, whatever, however you want to think about it, together and pull those out front, right? We're just using our distributive property here. This is just one binomial times a monomial, we're just distributing in. We get AX1 times probability of X1 plus B probability X1, putting all of our A's out front, all our B's at the end. Addition's commutative, so we're just using that here. We can factor an A out, and when we factor an A out, we see what's left is exactly the expected value of X. And when we factor a B out, we see what's left is probability of X1 plus probability of X2. Well, that's just the sum of all the probabilities, or that's just 100% or 1. So B times 1. So super nice little property of expected values is that it splits sums apart and constants can come out front. Constant multiples can come out front. For the variance, well, the variance of X is by definition the expected value of X minus mu squared. It's the average squared deviation from the mean. If I multiply out X minus mu all squared, remember this is a binomial squared, so I have a cross term. I got to be careful with foiling, right? If I have A plus B all squared, that's A squared plus 2AB plus B squared. So don't forget about that cross term. So expected value of X minus mu all squared is the X minus mu squared multiplies out to X squared minus 2 mu X plus mu squared. The expected value splits sums apart. So it's the expected value of X squared plus the expected value of negative 2 mu times X plus the expected value of mu squared. But mu squared is, well, that's just a number. Mu is just the number. It's the mean of the distribution. So mu squared is just a number. It's not a random variable. The expected value of a constant is just that constant. This factor negative 2 mu is just a constant. It comes out in front of the expected value out to here. And I noticed that, well, what's left over is the expected value of X, but that's just another name for mu. So I get minus 2 mu times mu, or minus 2 mu squared. So I have expected value of X squared minus 2 mu squareds plus 1 mu squared gives me a net minus 1 mu squared. This gives me another formula for variance, and it turns out that, at least I think, practically speaking, this one is easier to compute. Sometimes it might be easier to compute the variance directly this way, but I prefer this one in most cases, so I just use this one basically all the time. And as an exercise, you can do something that kind of combines these two ideas to show that the variance of ax plus b equals a squared times the variance of x. So in the next couple of class meetings, we're actually going to go through a couple of proofs. We're going to go through like the proof of Chebyshev's theorem, the proof of the law of large numbers, or a proof of the law of large numbers. There are a couple different laws of large numbers. And we'll talk a little more about expected value and variance there. We'll use some of these side notes, but these are also good things just to know in general. Variance of ax plus b, the multiplicative part of it gets squared when it comes outside of the variance. And actually the plus b doesn't have any effect at all, because that plus b is just shifting where the kind of where the weights are. It's just kind of shifting where these weights are, but not changing how spread out they are. So the variance, of course, shouldn't really care about the location. It cares about how spread out they are. But we can compute the variance as expected value of x squared, which remember just means that we square each outcome, multiply against its associated probability, do not square the probabilities. We still want the probabilities just as they are. They add up to 1. And then add all that together. And then, of course, the standard deviation is just the square root of the variance. Okay, so let's work off of a table like we did before. We have our probability distribution here. This is the example where we had X is the number of heads on one flip of an unfair coin. So we're just counting the number of heads. So X can be 0 or 1 with probabilities 0.3 and 0.7. The products are 0 and 0.7, and the expected value, or mu, was 0.7. Now, if I want to compute the variance, I have mu. I can figure out what mu squared is. I need the expected value of x squared. So I need to make a couple more columns. I need to make an x squared column. I don't know why these columns are so wide. There we go. I need to make an x squared column. And so I say, what is 0 squared? That's 0. And what is 1 squared? 1. And in this case, the x squared column turned out to be the same as the x column just by chance, because 0 and 1 squared are just themselves. Now I multiply the x squared column against the original probability of x column. Don't make a mistake here and try to square the probabilities or anything like that. Right? The probabilities add to 1. They're the things that give the weights. We're not squaring the weights. If we squared 0.3 and 0.7 and tried to use those as weights, they wouldn't add up to 1 anymore. We would be taking like a weighted average with weights that don't add up to 1, but we also wouldn't be dividing by the sum of the weights. That wouldn't be good, right? So we don't square the probabilities. So what is x squared times probability? 0 times 0.3 is 0. 1 times 0.7 is 0.7. And we add those together, we get actually expected value of x squared is 0.7. In this kind of a trial where our outcomes are only 0 and 1, it turns out that the expected value of x and the expected value of x squared happen to be the same number. Usually that doesn't happen though. What's my variance? It's this. Expected value of x squared. Again, don't like take this number and square it. The expected value of x squared, the squaring was already done. That's what we did in this column. So that's 0.7 minus the square of this. Mu squared is 0.49. And this gives me what? 0.21. And that is variance of x. And this variance should have in parentheses on it. So the variance gets parentheses. The expected value, sometimes people write it with parentheses, but most often it's written with these brackets. And to be completely honest with you, I've researched it before, I've looked into it, and as far as I can tell, nobody really knows why expected value has brackets and variance doesn't. There are kind of some pretty reasonable reasons from other areas of math why it would make sense for expected value to have brackets. But if we were going off of those reasons, we would think the variance would have brackets too, and variance just usually gets parentheses. So, but kind of just notationally, expected value often gets these brackets and variance does not. But it's not like the end of the world if you write your expected value with parentheses or your variance with brackets. So it's just one of those things that's more maybe historical status quo or something than anything else. Okay, so our variance is 0.21. And then what's our standard deviation? Well, let's come over to our calculator. So let me switch back to full screen. Come over to our calculator and we do second x squared to give me a square root of 0.21. And it looks like that gives me about 0.46 or so. So it looks like I have a mean of about 0.7 and a standard deviation of about 0.46. Just like in chapter 3, computing variances and standard deviations and so on, right? It's kind of like, it's really confusing to watch me do it or to do it the first couple times. By the time you get to the fourth or fifth time that you work through a problem, it starts to kind of make some sense. You're like, okay, I'm starting to see the pattern. By the eighth or 10th time you work through a problem, it's, it's a little more just like kind of turning the crank, and you know what the procedure is, you just go through it. So it's it's a lot to remember at first, but after you do it several times on the homework, it becomes a lot more manageable.
Can you run through that just one more time, please?
Yeah, we're going to go through a couple more examples.
Okay, thank you.
Yeah, definitely. Okay, so now let's look at our bet of $1 on the unfair coin. Let's see how that shapes up. So here we have X, our outcomes are minus $1, plus $1. Let me actually go ahead and put the unit in here as well, because I do want to make a point about units in a second here. Let me actually, because I don't want to carry that unit through to everything, I just put it like this. So remember that X is in dollars. And just like before, we did our multiplication across, our addition down to get our expected value of X, aka mu, was plus 0.4. And remember what that meant is kind of on average, when we average out over a lot of different plays of the game, we'll win about 40 cents per play. And that's in dollars. Why is that? Because I have dollars times unitless quantity tells me that this column is in dollars, and then I add dollars together to get dollars. Okay, so now let's do expected value, or sorry, variance, the expected value of X squared minus the square of the mean. Let's bring that formula down. So this is the next thing I need to compute, expected value of X squared. And just to remember, what is expected value of X squared? We take each outcome and we square it. Then we multiply each of those squared outcomes by their associated probability, the original probability, not the squared probability. And then we add all that together. So I start by squaring each outcome. Well, now -1 squared is +1, and 1 squared, of course, is also +1. I multiply the X squared column against probability of X column. So 1 times 0.3 is positive 0.3. 1 times 0.7 is positive 0.7. And once again, one note, it's connecting my decimal points. And I see that expected value of X squared is 0.3 plus 0.7, or exactly 1. When I have a situation like this, where my outcomes are either -1 or +1, my expected value of X squared always ends up being 1. Okay, so let's compute the variance now. We have all of our component pieces. The variance of X is expected value of X squared, or 1, minus the square of the mean, minus 0.4 squared. Or that's 1 minus 0.16, or that is 0.84. That is our variance. Now, if we track units through here, the X column is in dollars. So I have -$1 or +$1. The X squared column is in units of dollars squared. When I square my outcome, I get a square on the unit as well. My X squared probability of X column is in square dollars as well. So dollars squared. When I sum those, I get units of dollars squared. And my variance, just like in chapter 3, is in these annoying units of dollars squared that aren't really sensible, uh, you know, in light of our original problem and our outcomes and so on. When I take the standard deviation, just like before, I square root. I get square root of 0.84 dollars squared. This gives me about, let's see what that number is. Square root of 0.84. So that's about 0.92. And then square root of dollar squared gives me my original unit of dollars back. So just like in chapter 3 with the variance versus standard deviation, fixing the units, same thing goes on here. The variance ends up getting squared units, and going back to the standard deviation recovers the original units. So we're in a different context, but the idea with the units, with the variance and standard deviation, is still the same. Okay, let's look at this example, the number rolled in an unfair die. And here we're actually going to use Excel to help us out a little bit. Let me move this over a bit. There we go. So here I have my probability distribution, and I also wrote my X times P of X's here. So I entered my probability distribution in Excel. And as far as I know, I don't think Excel has a way to say, this is a probability distribution, find its expected value, or this is a probability distribution, find its standard deviation. But Excel can definitely save us some time with these calculations. So to find the expected value or the mean, I want to take my probability distribution. I just type these numbers in. They just are what they are. And now I want to use formulas. I want to multiply X times its probability. I want to multiply 1 times 0.1. And then again, remember, if I hover on the bottom right of the cell and double click, that'll copy that formula down in a relative manner. So this cell multiplies the two cells that are to the left of it. Oops, I didn't want to do that. There we go. So this cell multiplies the two cells that are to the left of it, as does this one. And then if I want to compute my expected value, let's right align that so it looks a little better. I'll add up these, that. Anymore, like Excel tries to be really smart and like make the text boxes easier to see, but I don't know why it always like covers up the thing that I'm trying to select. So C3 to C8, that does look right. I thought maybe I had the window too small or something, but I don't know. We'll just blame Microsoft. We blame Microsoft for everything. So expected value 3.8, and that was exactly what we found before. Now remember, what I want to do next is compute the squares of the outcomes, so that I can compute expected value of X squared. So I'll just take outcome and then caret shift 6. 2. So I want to take the second power of each of these 1 through 6. So 1 squared is 1, as I see. And then again, if I hover over the bottom right and double click, I see that those are the squares, 1, 2, 3, 4, 5, 6 squared. And again, I multiply each of these by the original set of probabilities. I don't want to square the probabilities or do anything funky with the probabilities. These probabilities are the weights that add up to 1. If I do anything to them, they're probably not going to add up to 1 anymore. That's a pretty clear sign that something has gone awry. Now, I'm not saying the reason we don't want to do anything with the probabilities is because they won't add up to 1. The reason is because that's how the definitions work and so on, but not adding up to 1 is a pretty clear sign that if you're doing a weighted average with weights that don't add up to 1 and you don't have a denominator, that's a pretty clear sign that something went wrong somewhere. But I take my squared outcomes, multiply by the original probabilities, and then copy that down. So that's like this column up here, this x squared p of x column. That gives me each of these terms, squared outcomes times probabilities. Then I add those together to get expected value of x squared. And get that E3 to E8 looks good. And this is the expected value of x squared. I put a little apostrophe here. The apostrophe forces Excel to think of whatever comes next as text because I was starting this with equal so that I could say it's equal to expected value of x squared. So just so you know, if you're following along with me, if you just type equals E bracket x caret 2 end bracket, Excel's probably not going to be too happy with that. Let's see what happens if it does that. Yeah, see, it doesn't like that. It thinks it's a formula. But if you type an apostrophe first, that says it forces Excel to think of everything after that as text. And no problem there. For our variance, we take expected value of x squared minus mu squared. So the variance of x is this number minus the square of this number. Right? 16.7 minus 3.8 squared. And we see that's about 2.26. And the standard deviation is the square root of that variance number, or about 1.5. So we have an expected value of just under 4 with a standard deviation of about 1.5 for this, for a roll on this unfair die. Any questions so far? Okay, so let's come back over here and take a look at this more general problem where we're counting number of heads on one flip of a coin. So just to be clear, X is the, why can't I find the pound sign? Number of heads on one flip of an unfair coin, where probability of heads is, well, we get X equals 1, we get 1 head, P proportion of the time. So we're just using the variable P here to represent the probability of getting a head. And so if 1 comes up P proportion of the time, then 0 has to come up 1 minus p proportion of the time, so that the two add up to 1, right? Because 1 minus p plus p, the minus p and the plus p cancel, and I just get 1. So if I'm looking for the expected value, I get 0 times 1 minus p is 0, and 1 times p is p. The expected value is just p. If I flip a coin, with an 85% chance of coming up heads, if I flip it a whole bunch of times, I would expect about 85% of the time I would get a heads, and about 15% of the time I would not get a heads. X squared, if I square 0 and square 1, they actually stay the same. X squared times the probability, 0 times whatever is 0, 1 times p is p. Expected value of x squared is p. The variance of x is the expected value of x squared, or p, minus the square of the expected value of x, minus p squared, or that's p times 1 minus p. And then standard deviation of x is square root of p times 1 minus p. And this is actually going to turn out to be an important distribution. This idea of getting 0 or 1, what we'll call successes on one try, or 0 or 1 heads on one flip of a coin. If we get a success, or if we get a head p proportion of the time, the mean, the expected value is p, and the standard deviation is root p1 minus p. And a little side note, we'll also use this in the future. Let me pop that onto a second line so we can see it there. We'll also use this idea in the future. We won't, the book doesn't exactly mention this by name, but there's this important idea in probability and statistics, and kind of in some sense more generally across science, of this idea of maximal entropy, or the law of parsimony, or Occam's razor. You might have heard it. It's probably most commonly called Occam's razor, but it's a little bit like if you have two competing models that both explain the same system equally well, you should choose the less complicated model. Because if I have a model where, only one assumption needs to be met for it to be true, or a model where 5 assumptions need to be met for it to be true, well, the chance that I can meet all 5 assumptions is probably less than the chance that I only have to meet one assumption, right? The more complicated the model, typically the more things need to be satisfied in order for the model to apply. And that's this idea. That's where this idea comes into play, this idea of maximal entropy. If we look at, a system, let's say, where I only know that there are 2 things that can happen. We'll call it either success or failure, where x can be either 0 or 1. Either I see the thing that I'm looking for or don't see the thing I'm looking for. If there are only 2 outcomes, and importantly, nothing else is known about the system, we should assume 50-50. In other words, by assuming 50-50, we, in some sense, kind of impose the fewest modeling assumptions on the system. We leave the model to be as free as possible to fit itself to the system in some sense. Well, what do I mean by that? Well, what I mean is that if we consider the variance, that's kind of, in some sense, a representation of how much unknown there is about the system. If I had a variance of 0, well, that would mean that, like, maybe either p is 0, like I can never get a heads, or p is 1, meaning I always get a heads. Well, then I know everything about the system. There's no unknown. I just either know that I never get a heads, or I know that I always get a heads. So the p's in between are the more interesting ones, right? It would be kind of silly to say, I know there are 2 possible outcomes. Let me just assume that one of them happens all the time and the other one never happens. If I look at a graph of the variance, as a function of P, the probability of success, if P is 0, the variance is 0. If P is 1, the variance is 0. If it's impossible to get a heads, I always get a tails. There's no variability in the system. There's nothing I don't know. If I always get a heads and it's impossible to get a tails, there's nothing unknown about the system. I always get a heads. If I only know there are two outcomes and I don't know anything else about the system, like that one of the outcomes is guaranteed, it would be kind of silly to model it at these extremes and to say, well, just assume that pick one of the outcomes and assume that one always happens. If we look at P minus P squared, as a function of P, this is a quadratic opening downwards, right? It's a quadratic because it has highest degree 2, and it's opening downwards because the coefficient of the P squared term is negative. I have two intercepts. It's going to be nice and symmetric about these intercepts. It's going to reach a maximum at P equals 1/2. If there are only two outcomes, then I know that my probability distribution has to look like this, P and 1 minus P for the two outcomes. And the question becomes, what should I choose P to be for my model? The most sensible P, in a sense, is 1/2. So kind of all the way up above where I mentioned this fallacy related to probabilities, where we say, if there are two possible outcomes, the chance is 50-50 is not correct in general. Well, that's not correct when we know other stuff about the system, right? If I know that I'm playing the Powerball, and I mean, assuming 50-50 chance that I either win the Powerball or don't win the Powerball is probably pretty silly because I know a lot about that system. I know that it's quite unlikely to win the Powerball. I know that there's a big payout if I win the Powerball, and lots of people play the Powerball, and not lots of people are multimillionaires. So I kind of know that the Powerball system is not 50-50. It would be kind of silly for me to model that as 50-50. But if I were to tell you, that here's some system and there are two outcomes, and that's all that we know about the system, we don't know anything else about it, then the most sensible model is 50-50. And we'll see when we start into, say, chapter 7 or 8, and we end up in a situation where we have to make an assumption. We want some criterion to be true about maybe some confidence interval. We want it to satisfy some characteristic. And we don't really know what the underlying probability P is for the system, and we're trying to find it. Well, the most conservative approach is to take P equals 1/2 because that's kind of the safest bet. It's the one that maximizes the variance that allows for the most variability in the system. And if the system is actually a bit less variable than we had predicted, that's probably just better for us, right? Our predictions are just going to be more solid, let's say, than we had expected. But we probably don't want to go the other way. We probably don't want to assume that the system's really not variable at all, not very variable. I don't know. And make a prediction, and then I find out that there's a whole lot more variability than we expected, and our prediction is just meaningless then. Okay, so I think we'll stop about there for today. When we come back next time, we'll probably do another 1 or 2 problems in 5.1. One thing that I tend to like to do if we have a more challenging topic like this one is split it up between 2 classes. So this gives you a chance to, go back, look through your notes, maybe try a couple of homework problems, things like that. Digest it for a couple of days, and then we'll come back and we'll do another example or 2 on Wednesday, and then we'll move on to 5.2 and 5.3. And that'll actually wrap up chapter 5. And next week we'll start into Bayes' theorem. So that is the plan. Are there any questions on anything?